Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about the module MOS capacitors from the paper Semiconductor Materials and Devices. So the learning objectives of this module are: first, we will be discussing about the ideal MOS device. Second, the biasing conditions of an ideal MOS diode. Third, the detailed analysis of surface space charge region. Fourth, the CV characteristics of ideal MOS capacitors were discussed. They will be discussed. Next, we will also discuss about the practical MOS, that is SiO2 Si MOS diode. And lastly, the interface traps and charges in oxides will be discussed. So students, let us start with the basic introduction about the module. Metal oxide semiconductor MOS capacitors exhibit the sophisticated characteristics when compared to the ordinary metal dielectric metal capacitors. It is the replacement of one metal electrode by a semiconductor that leads to some unique effects. So here the dielectric in the MOS capacitor has almost always been the silicon oxide or oxide for short, so that the standard term is MOS, metal oxide semiconductor. So the MOS capacitor can be seen as a structure consisting of two heterojunctions. First is metal dielectric and second is dielectric semiconductor. So where the dielectric is the silicon oxide. It is the high quality of oxide semiconductor interface that enables the practical applications of this device structure. For decades, a device quality oxide semiconductor interface has been limited to one semiconductor only, that is silicon. It is the fact that makes silicon by far the dominant semiconductor, in spite of the fact that many other semiconductors have better bulk properties. Recently, device quality oxide semiconductor interfaces have been developed on the silicon carbide, a wide range gap semiconductor with excellent bulk properties. So here the problem with the interfaces are due to the dangling bonds, the atomic bonds at the semiconductor surface, that we have to be electronically passivated to enable the existence of mobile charge at the semiconductor surface. Now, there are no special effects at the metal oxide interface. In fact, heavily doped polysilicon has been typically used in the place of metal electrodes, the reason being an important technological effect that relates to the MOSFET structure. Accordingly, the energy band diagrams will also be shown by the polysilicon gates. Now the MOS capacitors, they have been used in linear circuits and as the storage elements in random access memories, RAMs, and charge coupled devices, CCDs. So the real importance of this structure, however, is that it is the central part of the most devices in electronics, the metal oxide semiconductor field effect transistor MOSFET. The metal or heavily doped polysilicon of the MOS capacitor in a MOSFET is called as the gate. So accordingly, the metal polysilicon electrode of the MOS capacitor will be referred to as the gate, and the oxide will frequently be referred to as the gate oxide to distinguish it from the oxide layers that play other roles in integrated circuits. MOS capacitors. So students, metal oxide semiconductor, that is MOS capacitor, is useful in the study of semiconductor surfaces. It is most important device for VLSI MOSFET. So students, it is clear from this figure that it comprises of a semiconductor which may be N-type or P-type, having a thin oxide layer of thickness chi0 on its surface and a metallic layer which is known as a gate is also present on the surface of this oxide layer. The semiconductor has an ohmic metal contact which is generally at ground potential. So a voltage V is applied at the metal gate with respect to the semiconductor. Now the conditions for the ideal MOS diode or a capacitor are: first, the difference between the work functions of semiconductors and metal, that is phi s and phi m, is 0. Second, oxide is a perfect insulator and is devoid of any charges. Ideal MOS device. So students, we have already studied the conditions for ideal MOS device. This is the energy band diagram of an ideal MOS diode under zero applied bias, where we have taken the semiconductor as a p-type semiconductor. Now, as it is evident from the figure that on the metal side we have the Fermi energy level corresponding to E Fm, and this Q phi m corresponds to the work function, and this oxide layer is of thickness chi0. Now if we go towards the semiconductor side, then Eg is the energy band gap, Ei is the intrinsic energy level, Ef is the Fermi energy level, Ec corresponds to the bottom of the conduction band energy level, Ev corresponds to the top of the valence band energy level. Now here the P suffixes in all these corresponds to the p-type semiconductor. Now here Q psi Bp corresponds to Fermi energy with respect to the mid gap. Q phi Pm corresponds to metal to oxide barrier energy. So here M subscript corresponds to the metallic and P corresponds to p-type semiconductor. Now when applied bias is 0 to an ideal MOS diode, then energy difference between the metal work function Q phi m and the semiconductor wave function Q phi s is 0, that is, the work function difference Q phi ms is 0. Thus, the work function difference for p-type semiconductor can be expressed as Q phi MP is equal to Q bracket phi m minus phi p is equal to Q phi m minus bracket Q chi p plus Eg by 2 plus Q psi Bp bracket close equal to 0. Now here Q chi corresponds to the semiconductor electron affinity and Q psi Bp is equal to EI minus EF. EI corresponds to intrinsic Fermi level and EF corresponds to the Fermi level. So, the energy band is flat when V is equal to 0. That is, this is known as the flat band condition when no bias is there. The only charges that exist in a diode under any biasing conditions are those in semiconductors and those with equal but opposite sign on the metal surface. No carrier transport through the oxide under DC biasing conditions or resistivity of oxide is infinite. So, when ideal MOS diode is biased, that is a positive or a negative voltage is applied, there are three cases arises at semiconductor surface. So, we will discuss it later on, the three biasing conditions for an ideal MOS diode. The different biasing conditions of an ideal MOS device. First is accumulation, when the applied bias is less than 0. Second is depletion, when the applied bias is greater than 0. Lastly, we have the inversion, when a very high positive voltage is applied or the voltage is greater than the threshold voltage. So the first condition is accumulation, when the applied bias is less than 0, that is a negative bias is applied. So for a small and negative applied voltage, that is V less than 0, Fermi level on the metal side is raised by an amount QV than on the metal side. The schematic under this biasing condition is shown on the left hand side and the energy band diagram is shown in the figure on the right hand side. So, as you can see from this energy band diagram, that is, after applying a negative bias, this Fermi energy level is raised by an amount QV and all the energy bands are shifted upwards. Now, since phi m and chi remains unaffected by applied bias V, so the vacuum level on the metal side raises by QV and the bands near the semiconductor surface, they are bent upward. So no current flows in MOS irrespective of V. The Fermi level in semiconductor will remain constant. The vacuum level must bend up gradually to accommodate the applied V from semiconductor side. Since oxide is assumed to be charge-free, the lower edge of the oxide conduction band will bend linearly. The negative applied bias voltage on the gate implies that the negative charge on the gate producing equal and opposite charges in the semiconductor by attracting holes near the oxide semiconductor interface. Therefore, there is an enhanced concentration of holes. They occur near the semiconductor surface with a consequent upward bending of energy levels. This is known as surface accumulation condition. Now students, we already know that the carrier density in the semiconductor is P is equal to Ni multiplied by exponential Ei minus Ef by kT. So the upward bending of energy band causes the increase in Ei minus Ef, implying the enhanced concentration of holes near oxide semiconductor interface, which is called as the accumulation condition. Now here the depletion condition corresponds to the applied bias greater than 0. So for a small positive applied bias, the holes are pushed away from the oxide interface. Therefore, there is a formation of depletion region in semiconductor near the interface, having mainly the negative charged acceptor ions Na. This is known as the depletion condition, and the schematic under this biasing condition is shown in the figure on the right hand side, and the energy band diagram is also shown over here. Since hole concentration in depletion region is very much less than the concentration of holes in the neutral region of semiconductor, so the separation between EF and EV is increased at the interface, causing a downward bending of energy levels EC, EV and EI. So as you can see over here, that is, there is a depletion region formed, and the space charge per unit area in the semiconductor, that is the charge in the depletion region, which is the width of the depletion region is W, corresponds to QSC is equal to minus QNA multiplied by W, where W, as we know, represents the width of the depletion region and Na is the concentration of acceptor ions in the semiconductor. Now, for equivalent to the breadth of this depletion region, we have the height of this electrons accumulation at the metal oxide interface corresponding to QM. Inversion. Now this inversion happens for a large positive applied voltage, and there is a downward bending of bands occurs, and when EI touches the EF at the surface, the semiconductor surface becomes intrinsic. So for a large V, now as we are increasing the V, EI crosses the EF and conduction band becomes closer to EF instead of the valence band, that is the minority carriers, they are attracted to the interface. So semiconductor surface contains more electrons than holes. So this corresponds to that the surface gets inverted from p-type to n-type. The thin region chi I, where electrons concentration exceeds the whole concentration is called as the inversion layer. So, this figure on the left hand side shows the schematic under this biasing condition, and on the right hand side we can see the energy band diagram. So, in this biasing condition, the minority carriers Ns becomes more than the majority carriers. Now, as we know that the electron concentration in p-type material is given by Np is equal to Ni multiplied by exponential to the power Ef minus Ei by kT. Since Ei minus Ef is greater than 0 in the case of inversion, that is when Ei crosses Ef at large V, which implies Np at the surface is greater than Ni and Pp at the surface is less than Ni. Therefore, surface of p-type is inverted, and this is known as the inversion condition. So, once the inversion occurs at the surface, further increase in V will induce practically all additional negative charges in the inversion layer. So, students, let us now discuss a detailed analysis of surface space charge region of ideal MOS device when the applied bias is greater than 0. The electrostatic potential psi p is defined as 0 in the bulk of semiconductor. So at the surface, psi p is equal to psi sp, which is the surface potential. Now Ei minus EFP is equal to Q psi Bp for chi greater than equal to W for bulk, and Ei minus Ef is equal to Q psi Bp minus psi for chi greater than W bulk. So the figure on the right hand side shows the energy bands of p-type semiconductor surface in the ideal MOS device. Therefore, whole concentration P0 in the neutral semiconductor bulk away from the surface is P0 is equal to Na equal to Ni multiplied by exponential Q psi b P by kT. Now here assuming that all Na are ionized. So thus the electrostatic potential at the Fermi level psi Bp with respect to the intrinsic energy level Ei in the neutral semiconductor region is given by psi Bp is equal to kT by Q ln of Na by Ni. So similarly, the whole concentration in the semiconductor as a function of psi is Pp is equal to Ni exponential Q psi Bp minus psi p by kT. Now here psi can be replaced by psi p for p-type semiconductor, whereas electron concentration in the semiconductor as a function of psi p, that is in the space charge region, is Np is equal to Ni Q multiplied by psi p minus psi Bp by kT. Now here psi p is greater than 0 where band bends downwards. Also at the surface, densities are psi is equal to psi s, and the carrier densities using the above equations are Ns is equal to Ni multiplied by exponential Q psi s p minus psi b p by kT, and Ps is equal to Ni exponential Q psi b p minus psi sp by kT. Now here we can replace this Ni exponential q psi Bp by capital Na, that is the concentration of acceptor ions, multiplied by exponential minus q psi sp by kT. So we can infer that if the surface potential of p-type semiconductor in a MOS device is psi sp is less than 0, that is ps is greater than ni and ns is very much less than ni, so this represents the case of accumulation of holes where bands bend upwards for v greater than less than 0. Now psi sp equal to 0. This is the flat band condition, that is there is no bending of bands, and this is known as the equilibrium condition at V equal to 0. Now next is when psi Bp is greater than psi Sp is greater than 0. Now here Ps is very much less than Ni. So here there is a depletion of holes and bands bent downward. This is the case for V greater than 0. Next is psi Sp is equal to psi Bp, Ns is equal to Ps is equal to Ni, that is the intrinsic surface mid gap. Psi Sp is greater than psi Bp, Ns is very much greater than Ni and Ps is very much less than Ni. This is the condition for inversion, and there is a formation of inversion layer of electrons and bands again bend downward for V very much greater than 0. So the inversion condition is semiconductor surface becomes intrinsic when psi s is equal to psi b, that is EI touches EF, where Ns is equal to Ps is equal to Ni. The onset of inversion for the MOS having p-type semiconductor is given by psi sp is greater than psi bp. So strong inversion occurs when the concentration of minority charge carriers, that is electrons, at the surface Ns becomes equal to the concentration of majority charge carriers, holes, in the bulk Pb of the semiconductor. So the surface potential for strong inversion is psi p strong inversion is equal to twice of psi bp from equations G and C. Thus, the strong inversion is achieved when the intrinsic level EI at the semiconductor surface near oxide interface comes below the Fermi level as much as EI is above EFP in the bulk semiconductor. So students, let us now discuss the CV curve of ideal MOS capacitor. CV curve, that is capacitance versus voltage curve, is measured by superimposing a small AC signal, approximately 5 millivolt, on DC bias. So this figure shows the CV curve of an ideal MOS capacitor. That is, on the right hand side, we can consider the whole MOS device to be considered as the series combination of the oxide capacitance C0 and the semiconductor capacitance Cj, which is variable. And it is evident from this figure that the thickness of the oxide layer is chi0. So in the accumulation regime, that is when V is less than 0, that is no depletion region, the total capacitance is approximately equal to C naught, that is a constant, which is equal to epsilon oxide by chi naught. So, in this accumulation region, Cj becomes very large and MOS capacitance is a constant quantity approximately equal to C naught. Now comes the depletion regime, where the change in the C in response to the applied signal is due to the flow of majority carriers, that is holes in p-type only. They move in or out of the space charge region. So C naught is frequency dependent as relaxation time of majority carriers is small. So in the depletion region, that is V greater than 0, W increases with V and Cj is epsilon S by W decreases, and it results in the decrease in C with V. Now let us discuss the CV curve of ideal MOS capacitor for the inversion condition. So as you can see, students, that in the inversion regime, it is frequency dependent. In the inversion regime, charge flow in response to the applied signal may also occur by the movement of minority carriers between the inversion layer and the neutral semiconductor. So the MOS shows frequency dependence. If frequency is low, so that the generation recombination rates in surface depletion region are equal or faster than the gate. So voltage variation, then minority carriers can follow the applied signal and leads to the charge exchange with inversion layer in step with the signal. That is, for low frequency F1, it increases and then becomes constant, and for frequency F2, it is lower than F1, and for high frequency, it remains constant to the value Cmin. So in the later slides, we will discuss the frequency dependence of CV curve of MOS capacitor in the inversion regime. Now students, let us discuss the frequency dependence of CV curve of MOS capacitor. Now in low frequency, which is represented by curve A in the CV curve, the generation recombination rates in depletion region are equal or faster than the variation in the applied voltage V, implying that the minority carriers follows the applied signal and leads to charge exchange with the inversion layer in step with the signal. Now here W equal to Wm and electron goes to the inversion layer. So here, since C inversion is very much greater than C naught, because Wm is very much greater than L naught, so C inversion is the inversion layer capacitance and C naught is the depletion layer capacitance. C is approximately equal to C naught because C inversion is very much greater than C naught. Next is at higher frequency. Now for small AC signal, thermal generation cannot create the minority carriers fast enough to support a variation of charge in the inversion layer with applied V, implying that CV in the inversion part is different. So the variation in V, let us say delta V, results in the variation in the depletion region and the depth, that is W max plus minus delta W, where delta W is the small modulation in W due to applied bias as the AC gate bias delta V. Now here C is in series combination with C naught, and this C naught is equal to epsilon S by Wm, and C naught is almost constant and hence giving the low and the constant value of C, because Wm is large and C naught is low. Till now we have discussed the ideal MOS capacitor. So students, let us now discuss the practical MOS, that is SiO2 Si MOS diode. In practical MOS device, the difference in the work function of metal and semiconductor is not zero. That is phi ms equal to phi m minus phi s is not equal to 0 at Vg equal to 0. Secondly, the interface traps and the charges are present in the oxide layer. So as you can see in the energy band diagram, at thermal equilibrium, the phi m minus phi s is less than 0. It is not equal to 0. Whereas Q phi ms equal to Q phi m minus Q phi s is equal to VFB, which is nothing but the flat band voltage. Let us now discuss the interface traps and the charges in oxides. So following are broadly the charges and interface traps in SiO2 Si MOS structure. So these are interface trapped charge QIT, fixed oxide charge Q fix, oxide trapped charge QOT, and lastly is the mobile ionic charge Q mobile. So let us now discuss the interface trapped charge. Interface trapped charge QIT, they are due to the Si-SiO2 interface properties and lies in the forbidden gap. It is dependent upon the chemical composition of the interface. Now the interface trap density is orientation dependent. Let us say for an example 100 orientation, it is smaller than in 111 orientation by about an order. Now let us discuss the second part, that is the fixed oxide charge. Fixed oxide charge, that is QF, it is within the 30 angstrom of Si-SiO2 interface and cannot be charged or discharged over wide variation in surface potential psi s, that is, it is fixed. Generally, QF is positive and depends on the oxidation and annealing and on silicon orientation. When oxidation stops, some ionic silicon is left near the interface, resulting in positive fixed oxide charge. Oxide trapped charge. Oxide trapped charges QOT, they are associated with the defects in SiO2. These charges can be created, for example, by radiating with X-rays or high energy electron bombardment. Most of the process related oxide trapped charges can be removed by low temperature annealing. Next is the mobile ionic charge. The mobile ionic charges QM, such as sodium or other alkali ions, are mobile within the oxide under high temperature and high electric field operation. It may cause stability problems in the device. So students, let us summarize what we have learned in this module. First, we discussed about the ideal MOS device. Second, the biasing conditions of an ideal MOS diode were discussed in detail. Thirdly, the detailed analysis of surface space charge region was discussed. Next, we discussed the CV characteristics of ideal MOS capacitor. The practical MOS SiO2 Si MOS diode was also discussed. Lastly, we also discussed about the interface traps and charges in oxides. Thank you.